This brief presentation will give you a clear understanding of Schrödinger's wave mechanics. How quantum wave concepts were added to the modern theory of the atom structure. You will understand how electron orbital shapes create shells and subshells for all the elements of the periodic table. Niels Bohr embraced Max Planck's concept of quanta. He viewed the atom as electrons located at different distances from the proton, revolving around the proton nucleus, similar to the planetary system. The electrons at different energy levels, or quanta, are principal quantum numbers, designated by the letter n. These are integers, equaling 1, 2, 3, and so forth. Charles Barkla, the X-ray spectroscopy specialist, designated the electron energy levels as K, L, M, N, and so forth, to reflect the historic X-ray series performed. The Bohr model could not explain all the spectral lines. Spectral lines of other elements were observed, such as helium. Arnold Sommerfeld extended the Bohr model to explain the thin spectral lines ignored by Niels Bohr. He developed the atom shell orbital theory. He viewed the principal quantum levels as thin discrete layers, like the shell of an egg, containing minor elliptical orbitals within each quantum level. These additional orbitals consist of a quantum orbital for its shape, noted as the letter L, and magnetic quantum, for orientation M, noted as M sub L. An additional quantum number was discovered when Otto Stern and Walter Gerlach directed a silver atom beam through a non-uniform magnetic field. The beams should create one spot on the photographic plate. However, the photographic plate revealed two lines formed. Samuel Goudsmit and George Uhlenbeck interpreted that the two lines are formed by two electrons spinning with opposite rotation, adding a fourth quantum number for electron spin. By 1925, the model of the atom consisted of electrons having unique four quantum numbers. The principal quantum number designates the energy level of the electron, which is determined by the distance from the proton. Within that shell, there are three quantum numbers. The orbital quantum number establishes the orbital's shape. The magnetic quantum number establishes the orbital orientation. The spin quantum number establishes the electron spin. Examples of electron configuration are illustrated when the principal quantum number is increased and the shell's respective orbital and the magnetic quantum numbers are calculated. When n is equal to 1, L is equal to n-1, or 1-1 equals 0. The orbital quantum number, L, is 0 and the magnetic quantum number, m sub L, is also 0. The electron orbital designation is S, for sharp. If n is equal to 2, then L is equal to 1, m sub L can have three different orientations. The electron orbital designation for this electron configuration is P, for principal. If n equals 3, then L equals 2, and m sub L may have 5 different orientations. This electron orbital designation is D for diffuse. As the principal quantum numbers increase, the shape and orientation become significantly more complex. In the case of n equals 4, L equals 3 and m sub L has 7 different orbitals, with an orbital designation, F, for fine. Wolfgang Pauli determined that each electron is unique, identified by these 4 quantum numbers, and each orbital can only have 2 electrons. Louis de Broglie postulated if light can act like a particle, then particles can act like light, having the properties of waves. De Broglie's theory was embraced by Albert Einstein. The Davison and Germer experiment demonstrated the wave nature of the electron particle. Erwin Schrödinger proposed, in principle, a very simple equation. The kinetic energy, plus the potential energy, equals the energy of the electron. The Greek letter psi gives the electron location in space relative to the proton. By expanding, we have the wave function. With psi, the electron location changes in space, plus the mass of the electron, times the quantity of quantized energy of the atomic system, minus the potential energy in 3 dimensions. Werner-Heisenberg's uncertainty principle states that the location is not deterministic, there is only the probability of the electron location. Schrodinger equation solutions provide a better defined shape of the quantum orbitals. Here are the electrons' probable locations for the s, p, d, and f orbitals. The shell and subshell atom structure is further simplified by placing the principal quantum number, n, in front of the subshell designation. When n is 2, then the subshells will have 2s, with 1 orbital in the subshell, or 2p with 3 orbitals in the subshell, with a total of 4 orbitals in the shell. When n is 3, then the subshell will have 3s, with 1 orbital in the subshell, or 3p with 3 orbitals in the subshell, or 3d, with 5 orbitals in the subshell, with a maximum of 9 orbitals in the shell. Let us review the shell and subshell notation for elements used in the periodic chart. Here are the s orbitals. Note neon has the 1s orbital filled with 2 electrons. The d orbitals, the p orbitals, and the f orbitals. Another way to illustrate electron orbital subshells is to use the box notation. Each box may contain a maximum of 2 electrons and their spin. It also shows empty boxes for vacant orbitals in that shell. Lithium has 2 electrons in the 1s orbital, and 1 electron in the 2s orbital, with the 3p orbitals empty. In beryllium, the 1s and the 2s orbitals are filled, while the 3p orbitals are empty. In boron, after 1s and 2s orbitals are filled, then the first p orbital is filled. As the atom's number of electrons increased, Friedrich Hund developed rules for filling the orbitals. In 1925, Hund's Aufbau concept states that the electrons fill the lowest energy orbitals first, and then move up to higher energy orbitals, only after the lower energy orbitals are full. In addition, every orbital in a sublevel is singly occupied before any orbital is doubly occupied. All of the electrons in singly occupied orbitals have the same spin. In nitrogen, the p orbitals are half filled. The 3 electrons in the 2p subshell will fill all the empty orbitals first, before pairing, that is, adding the second electron to fill the orbital. Oxygen with 8 electrons fills the 1s, the 2s and adds 1 electron, with same spin, into each of the p orbitals, then pairs the 8th electron into one of the p orbital axis. Fluorine with 9 electrons fill the 1s, 2s, then the 2 electrons pair the 2p orbitals as shown. Neon with 10 electrons fill all the orbitals, resulting in a noble gas, like helium, is chemically inert. In summary, the elements of the periodic table are grouped based on the 4 quantum numbers filling the s orbitals. The d orbitals, the p orbitals, and the f orbitals.